Building a GA144 controlled robot. Taking the first step. A mobile robot consists typically of several parts: a power source, two gear motors, sensors such as infrared or ultrasonic proximity detectors, and communication system. All these parts are controlled with a single MCU running one control program. No parallelism is possible except for time-sharing multitasking. Unlike a robot with a single MCU, GA144 allows to dedicate individual nodes to specific tasks. A bunch of nodes then functions as a control module. The encapsulation of the internal function of the module simplifies the assembling of the modules together. The modules communicate via wire nodes or using a message passing mechanism. The interconnected modules then form the whole controller. The advantage of such a control system lies in its extreme flexibility. Any change of the architecture required can be done in software. We can even change the internals of the control system on the fly as the conditions are changing. GA144 also provides a true parallel computation. A robot with the differential drive has two motors with control modules. For the rest of the control system, such a module is like a black box. The only input to the module needed from the outside is demanded speed. The module then sets the driving voltage to the motor, usually as a PWM duty cycle, and checks the actual speed of the drive wheel using incoming pulses from an incremental encoder. The control process itself takes place inside the module, and the outside system does not need to know how this is done. The only output from the module to the rest of the control system is a distance traveled so far. This modularity allows development and testing the code without the real robot. Instead, an evaluation board or even SoftSim can be used. We do not need to write a special code to test our module. GreenArrays IDE already provides all we need. In a sense, testing the module is equivalent to testing a new word in Forth. This is what is great about GA144. We can use IDE to reach inside our module, to change its variables and even the code while it is running, since everything is stored in the node's RAM. The subject of this talk is the motor driver module. The entire module consists of four nodes. The nodes 317 and 217 are used since they both have access to the GPIO pins. The node 317 uses this pin to provide a PWM waveform to drive the motor. The node 217 uses the pin as an input of a signal from an incremental encoder. The other two adjacent nodes implement a PID regulator and an odometer. Except for the driver node, all other nodes are suspended in reading ports. The driver node's program is composed of an endless loop performing three tasks: measuring time intervals, passing data between adjacent nodes, and PWM waveform generator. The two values on the stack are the generator counter and the duty cycle. Depending on the duty cycle, the output pin is driven either high or low. The time intervals are measured using a free-running timer. In each cycle of the loop, a counter variable CNT is incremented with the word CNT+. The timer counts up to 1 FFFF hex and stops. There is no rollover of the counter. The word CNT0 is used to clear the timer. The code within the loop also tests both write and down pause for any activity from the adjacent nodes. It is done by reading the I/O register. Shifting its value left one bit at a time changes the sign bit. Since the activity flag is either 0 or 1, the value must be inverted before each bit is tested with the -if instruction. The content of the I/O register is copied onto the stack. All 4 bits are tested consecutively. If set, the corresponding code is carried out. We will discuss this part of the code in more detail later. After the last test is finished, the value is dropped from the stack. The node 217 is waiting for a signal from the encoder. It reads the left port and suspends until the level on the pin is as specified by the wake-up bit in the I/O register. Setting the bit to 0 makes the read suspend until the pin is high. When set to 1, it suspends the node until the pin is low. We are now ready to follow the flow of signals between the nodes. We will see how individual nodes come from the suspended state upon activity at a port, what code is executed as a response, and when the nodes suspend again. A burst of activity in suspended nodes starts with the detection of the falling edge of encoder pulse by the node 217. The node wakes up and is about to read the current timer value from 317 via the down port. Since 317 is not writing to the port yet, 217 suspends until the data is ready. Meanwhile, the node 317 tests the write and down ports for any activity. Finding that the node 217 wants to read, it writes the current timer value to the down port. This is the exact moment when the timer counter of 317 is reset to 0. The current timer value is passed through a filter to remove noise. We will say more about the filter shortly. The filtered value is then written back to the down port. As the node 317 is not ready for reading, 217 suspends once again. The node 317 needs to go through the port tests again to find out the 217 has something to write to the port. The node 317 reads the value from the down port. The node 217 then sends a signal leftwards to the node 216, where an odometer is implemented. Writing to the right port of 216 wakes up the node, and it increments an odometer counter. One little step of the robot is thus recorded. The node 217 performed its last action, and it goes back to the suspended state while waiting for another falling edge of the encoder signal. Let's see now how the node 217 implements all its tasks. From the preceding description, we know that the code runs in an endless loop. It is implemented in the word go, which calls repeatedly the word edge. The word edge uses the leap-then control structure. When the word leap is encountered, the execution continues beyond the corresponding then. Upon reaching the written instruction, it goes back beyond the leap word, and the code is executed again. The execution of the word edge starts by putting 800 hex onto the stack and leaping forward. The value from the stack is stored into the I/O register. In the present case, it sets the wake-up bit to 1, and therefore the following reading of the left port suspends the node until there is a logical low on its pin. The value read from the left port is dropped from the stack immediately, as required by the design of the F18 computer. Then the execution of the code returns back beyond the leap directive. There are two words to be executed: EMA, which stands for an exponential moving average, a type of infinite impulse response filter, and odo, meaning the odometer. The exponential moving average is calculated according to the following formula, where I is the input signal, O is the output signal, and W is weight, or a smoothing factor. In our case, we use quite a strong factor of 0.9. Smooth signal with low noise level is necessary for the calculations used in the PID regulator, as we will see later. The effect of applying the filter on noisy data is shown in the graph. We will see later how the odometer implemented in the node 216 functions in detail. For the time being, it is sufficient to know that the signal for the odometer is an arbitrary value sent to the node 216. Hence, the top of stack is duplicated and written to the right port. In order to implement the EMA filter, we need some auxiliary words. The first word is a simple 1+, which increments value in the T register. The next one is a fractional multiplication with rounding *.r. The word calculates with fractional numbers, where the 18-bit value is a signed number in the range from 0 to 1 exclusive, with the MSB being the sign bit. As the calculations are valid for positive numbers only, the MSB is always set to 0. The word *.r expects a positive fractional multiplicand in the S register and a positive integer multiplier in the T register. The multiplier is moved to A and T is set to 0, the initial condition required by the word +*. The multiply step is called 17 times within a 4 micronext loop. The product is a 36-bit number with a 17-bit integer part in T and an 18-bit fractional part in A. The bit T17 is a sign bit and is always equal to 0. The bit A17 is the MSB of the fractional part and it represents the value of 1/2. The rounding takes into account the value of this half bit. If set, the integer part in T is incremented by 1. Otherwise it stays unchanged. We are now ready to explore the calculation performed by the word EMA. The word expects two values on the stack, a weight W in S and the last output of the EMA filter O' in T. Out of reset, these values are set to 0.9 decimal for the weight and 1 FFFF hex for O', which is the maximum positive number. Calling *.r, we get a product of the weight and the last output in T. Note that the value of weight in S stays unchanged. Next we copy the weight on top of stack and the following code calculates the required expression 1 minus weight. Now comes the part when the node 217 reads the current value of timer counter from 317. The A register is loaded with the address of the down port and a fetch instruction gets the input data on stack. The second *.r instruction then calculates a product of the input value and its corresponding weight factor. We get rid of now disposable factor from S and sum the two products together. The resulting output value is duplicated to be used during the next execution of the word EMA, and it is written back via the down port to the node 317. Note the two instructions moving data between the nodes 217 and 317 being a part of the word EMA. The last part of the word edge is used to get past the rising edge of the encoder signal. A 0 value is stored onto the stack and the execution of the following code is repeated. This shows how the leap-then control structure can be used to shrink the code. Since this time the wake-up bit is set to 0, the left port reading suspends the node until the level on the pin is high again. This ends the execution of the word edge and it returns back to go, which restarts the whole loop again. Now we can finish the discussion of the code in the node 317. We already know that this node is constantly executing a timing loop. We also know that within that loop, the right and down ports are tested for any activity. In order for the loop to be running uninterrupted, a temporary storage for data being passed between nodes is needed. Such a buffer is defined by the words buff and buff store. This code shows a way of defining variables in array4. There is also a third word, buff0, which is used to clear the buffer. After incrementing the timer counter by calling the word CNT+, the content of the I/O register is put temporarily in T, and the bits corresponding to the activity at ports are tested as discussed earlier. In the following, only the code enclosed within the "-if then" clause is shown for the sake of clarity. Although the bits are tested in the order given by their position in the I/O register, this is the write port before the down port, we will start with the down port, as this is the port communicating with the node 217 already described. First, the A register is loaded with the down port address. In case the node 217 is suspended while reading the down port, the current timer counter value is written to the port, and the counter is reset to 0. If 217 is suspended while writing to the down port, the value is read from the port and stored into the buffer. When testing the write port activity, the A register is loaded with the write port address. In case the node 316 waits suspended while reading the write port, the value stored in the buffer is written to the port, and the buffer is cleared unless it is already equal to 0, in which case nothing is written to the write port, and the node 316 stays suspended. Thus, only a valid timer counter value stored in the buffer is sent to the node 316. The sequence of directives ahead, swap, then, in the colors shown here, enclosed within the if-then directives, functions as an else directive in the standard if-else-then control structure. In case the node 316 waits suspended while writing to the write port, the contents of the T and S registers are temporarily stored on the return stack. The write port is fetched, and the two values from the return stack are moved back. The net result of this operation is that the PWM generator increment is replaced with the new value provided by the node 316. There are two subtle points to be clarified. The first is the content of the buffer buff. We have already shown that between two consecutive falling edges of the encodered signal, the timer loop makes a certain number of cycles. The longer the interval between the edges, this is, the slower the movement of the encoder, the higher the number of cycles counted. It follows that there must be a minimal number of cycles counted, and that this is a non-zero value even at the maximum speed of the motor. Thus, a 0 stored in the buffer buff is a flag notifying the system that the node 217 is still waiting for the falling edge of the encoder signal. As we shown earlier, the whole process of reading the timer count is started by a falling edge of the encoder signal. However, what happens in case the signal from the encoder is constant, for instance due to the fact that the motor is halted? In that case, the timer would run up to 1 FFFF hex, and the whole controller would become deadlocked. To avoid this fatal state, the code for the word CNT plus needs a little modification. Instead of dropping the overflown value 20,000 hex, it is inverted, resulting in 1 FFFF hex, and it is stored into the buffer. The buffer now contains a non-zero value corresponding to the maximum time interval that can be measured by the timer, even if there was no falling edge of the encoder signal. And this value can be passed to the node 216 when demanded. This keeps the module responsive and under control of the higher level program. The second modification is aimed at reducing the energy consumption in cases when the module can be stopped entirely. Such a situation occurs, for instance, when the robot halts. With the code already presented, the timer and PWM loop is constantly running, even if zero speed of the motor is demanded. The modification exploits the fact that the PWM increment may be a positive number only. Therefore, We use a negative number as a signal for the node 317 to stop the PWM generator with logical low level set at the output pin and to stop the timer loop. We define a new word PWDN, which stands for power down, starting in the middle of the test of the right port being written to. After the contents of T and S registers have been stored on the return stack, the value from the port is fetched. Upon fetching the value from the right port, it is tested with the -if test. If negative, the value is dropped from the stack. 20,000 hex is written to the I/O register, driving the output pin to logical low, and the execution jumps to the beginning of the word power down. Here, the node 317 wants to read the right port again. Until there is a new value provided by the node 316, the node 317 stays suspended while reading the right port, and the energy consumption drops to its minimum. To wake up the node 317, it is sufficient for the node 316 to write a positive value to the right port. Upon that, the value is read by the node 317 as a new PWM increment. The two values from the return stack are moved back to S and T registers, and the node 317 continues executing its code. We shall now examine the node 316. Out of reset, the node is suspended in reading data from 317. The data provided by 317 is the filtered value of timer counter, which represents the current speed of motor. In the following part, we will be referring to speed of motor expressed as the number of timer cycles between two consecutive falling edges of the encoder signal. Strictly speaking, this quantity should not be named speed, as the relationship between the rotational speed of motor and this quantity is inversely proportional. However, we use the term speed here for the sake of simplicity. When the node 317 finds out that 316 is waiting suspended to read the port, and the current speed is available in the buffer in 317, it writes the speed to the right port. 316 then performs PID calculations and is ready to write the updated PWM duty cycle back to the node 317. The 316 then suspends until the node 317 is ready to read the data. Following that, the node 316 checks its left port for any message waiting. If there is a message, the node reads it, and based on its content, other actions can be taken, such as the demanded speed updated. Finally, the node suspends again while waiting for another speed data from the node 317. We shall now examine the code for the PID regulator. The theoretical background of the PID regulator is described in the corresponding application note AN016 and will not be presented now. The PID controller requires two input quantities as explained earlier. One is the demanded speed, Wk, the other is the actual speed, Yk. The indices k emphasize the fact that discrete quantities measured at a data point k are used. It is similar to a t-index used when continuous quantities at a given time are referred to. The regulator calculates a difference between these two values as an error Ek. The output of the regulator is called a control function Uk, which in our case is a PWM duty cycle for the node 317. The calculated Uk is such as to decrease the error to 0 as fast as possible and keep it there. The incremental PID regulator does not calculate the current value of Uk. Rather, it calculates an increment to the control function delta Uk, which describes a change needed for the Uk to reflect the current error Ek. Note that the value of delta UK is signed and can be either positive or negative. The calculation is carried out according to the following formula, which describes the discrete incremental PID regulation equation. The symbols EK, EK-1, and EK-2 represent the last three errors. The equation thus takes into account the recent history of the regulated system. The symbols Q0, Q1, and Q2 represent three parameters that have to be found experimentally in a process called regulator tuning. In our system, the values Q0 and Q2 are positive numbers, while Q1 is a negative number. The code for the node 316 starts with a definition of a double precision variable U. The variable is defined as two single precision variables in the node's RAM. The high part of the variable is defined with the words uHigh and uHigh store. Since we need to access the same word in RAM also in the extended arithmetic mode, we defined other two words, extended uHigh and extended uHigh store, with the extended arithmetic mode on. The difference between uHigh and extended uHigh is that when the latter is called, the extended arithmetic bit, this is the address bit 9, is set to 1. Otherwise it is cleared. The low part of the variable u is accessed in the same way using the words ulow and ulow store, or extended ulow and extended ulow store. Next we define some arithmetic words, the increment 1 plus, and an integer multiplication star. This word expects two 18-bit numbers in T and S. After the multiplication has finished, the 36-bit long result is stored in T and S, with the high-order word in S, while the multiplicand rests below it on the stack. Finally, we have a word MAC, which stands for multiply and accumulate. It expects two 18-bit numbers on the stack, a positive multiplier in T, and a signed multiplicand in S. The result of the multiplication is added to the variable u. Note that this word is also defined with the extended arithmetic bit set, hence the additions are carried out in the extended arithmetic mode. The heart of the regulator code is defined in the word PID. It expects two older errors already on the stack and the current speed in T. Its execution starts with fetching the value from the address 13 hex, which is a memory cell containing the demanded speed -1. The following instructions then calculate a difference between the actual and the demanded speed, the error EK. The following three lines of the code calculate successively three terms of the regulation equation. The three constants are the optimized parameters Q0, Q1, and Q2. First, Q0 times EK is calculated and added to the variable u. The error EK is temporarily stored on the return stack, and EK-1 is negated. Next, Q1 times minus EK-1 is calculated and added to the variable u. The error EK-1 is negated again and stored on the return stack. Finally, Q2 times EK-2 is calculated and added to the variable u. The two errors stored on the return stack are moved back. The variable u now contains an updated value, and three latest errors are on the data stack. Note that with each calling of the word PID, the errors are pushed one position down the stack and never removed from it. Here we have another example of how clever is the design of the F-18 computer in using circular stacks. The following part of the code is intended to get the updated U function within acceptable limits. These limits are given by the range of the PWM duty cycle. This is from 0 to 1 FFFF hex. First we test whether the new U value is negative by testing the sign of its high-order word. In such a case, the control value has underflown and is set to 0 as the lowest possible value of U. 0 is also sent back to the node 317 as the updated duty cycle. If positive, the high-order part of U is cleared and the low-order part is tested for overflow to the bit 17. If overflown, the value is set to the upper limit of 1 FFFF hex. Otherwise, the calculated U is within limits and is sent to the node 317 via the right port. The code in the node 316 begins execution at start. It just clears the carry bit of the extended arithmetics and falls through to go, which is an endless loop. In the loop, the node suspends while reading the right port. It stays in the suspended state until the current speed is sent by 317. With the current speed in T, the word PID is called, the updated duty cycle for the PWM generator calculated, and sent back to the node 317. What follows is a code for reading modified ganglia messages. It tests the left port for being written to. If true, the execution from the left port is called, otherwise the loop returns to go. The modified ganglia messages are described in the application note. It allows to set the demanded speed by writing to the address 13 hex. It can also be used to read the value of the control function U, the latest error EK, or even to set directly the PWM duty cycle, and so forth. It is also used in sending the power down signal to the node 317 in the form of negative PWM value. In general, the code via the left port can read or modify any RAM location, or even the values on both stacks. This demonstrates the true power of port execution, as all these tasks can be carried out while the whole motor control module is running and performing its duties. We have already seen how the node 217 writes to the left port as a result of a falling edge of the encoder signal. This wakes up the node 216 and an odometer counter is incremented. We shall now inspect the code of the node 216. A variable odo holds the count of falling edges of the encoder signal. This number can be easily converted to the number of motor revolutions and therefore to the distance traveled by the robot. The word odo plus is used to increment the variable odo. The main code loop is defined in the word go. The A register is loaded with the address of the right port and the register B points to the I/O register. Both values are set in a boot descriptor. Fetching from the right port then suspends the node until the node 217 writes to the port. The value read is left on the stack as it is a dummy word. The counter odo plus is incremented and the code tests the I/O register if the left port is being written to by the node 215. The left port is an entry point for a ganglion message. If active, the first word from the left port is read, which is a focus call whose execution we want to avoid, and then an execution from the left port is initiated. The ganglion message can be used to read the content of the counter odo or to clear it by writing a 0. When finished, the execution returns back to the word go. And so we have covered the last node of the motor control module. At the beginning of our presentation, we have explained that a mobile robot needs two motor control modules in order to provide a differential drive. We have explored the module internals, and we should now look at the possibility to place the modules inside the GA144 chip. The module for the right motor can be placed in nodes 217, 216, 317 and 316 as shown earlier. The second module can be conveniently placed right above the first one in nodes 517, 516, 417 and 416. Note that the second module is a mirror image of the first one and is symmetrical along the line between the rows 3 and 4. Thus, the motor control modules form a cluster near the right edge of the chip. The communication ports to the modules are located on the left side of the cluster and therefore are accessible from Polyforth, for instance via Ganglia message or from the GreenArrays IDE. In order to demonstrate that almost any code for GA144 can be developed and tested in the software simulator, we are now going to show how the whole module runs in SoftSim. For this demonstration, we have used a testbed providing a square wave signal which simulates pulses from an encoder. After initialization of all nodes, only 317 is running, while the other 3 nodes are suspended reading from ports. The PWM generator is toggling the levels on the output pin. The node 217 waits for the falling edge of the encoder signal. When it comes, the node starts executing until its result is passed back. Then the odometer receives a signal and wakes up. Next, 316 reads the speed, calculates a corrected duty cycle and sends it back. The burst of calculations has finished, and except for the timer and PWM generator, all the nodes are suspended. There is a short wake-up of 217 when a rising edge is detected, and then it awaits a falling edge in the suspended state again. We now accelerate the video 4 times so you can appreciate the time distribution between executing and suspended state in nodes. Watch how a falling edge on 217 starts the burst of action, which is quickly replaced by a longer period of inactivity. No experiment can be entirely replaced by a simulation. Therefore, we have carried out a series of tests with a GreenArrays evaluation board controlling a brushed DC motor. We have used an optical encoder and an electromechanical brake controlled by a Polyforth program. The setup is described in detail in the application note. The experimental run consisted of several steps. First, the motor was started and its speed stabilized. Then the control program written in Polyforth counted 8 encoder wheel revolutions and a signal was sent to the brake. The brake was activated for another 8 revolutions and then it was released. The last part took another 8 revolutions and the motor was turned off. There were 2 rounds of experiments. First unregulated with the PID regulator off, the second regulated with the regulator on. During each experimental run, the actual speed of the motor was recorded. The result of the unregulated run is shown in an orange trace. A dramatic decrease in speed is shown when the brake is applied. The speed increases incrementally after the brake is released. On the other hand, the regulated run shown in a green trace demonstrates clearly the regulator in action. The speed of the motor is almost constant, slightly oscillating around the defined set point. We have confirmed our design experimentally. I would like to thank GreenArrays for their support, particularly Greg Bailey for providing me with the evaluation board and Charlie Shattuck for invaluable discussions about programming GA144. And thank you for your attention.